S. Chan presents Educational Video Lectures. Difficult concepts made easy. Study anywhere, anytime.
How we can implement the logical devices or the logical gates into the digital devices. So what is the main application of the logical gates and how we can develop the new logical devices, digital devices that can be maintained, that we will understand in this topic.
If you want to study this topic in detail, refer to the book by S. Chan Publishing. Link is provided in the description box.
So myself, Dr. Narendra Kaur, welcome to S. Chan Academy. So let us begin. What are the application of logical gates and how the logical gates are used to convert the analog signals to the digital signals. So now next is the application of logical gates. So logic gates, these have lots of application, but mainly based upon their mode of operations or on their truth table. Because in the truth table, we can get the output values. So depending upon a requirement, the different kind of logic gates that can be used. So when we are getting the, by giving only input to the one port and we want the output to will be there, then the OR gate is preferred. And when we want by giving the input to the both of the port, then we want the output, then in that case AND gate will be preferred. So depending upon the truth tables, we can use the logical gates into the different digital devices. So they depending upon the truth tables and the mode of operations. So like mode of operation means how we can combine the different logical gates like XOR gate, exclusive NOR gates. So different kind of digital circuits that can be maintained. So basic logic gates are often found in the circuits such as safety thermostats, push buttons lock, automatic wiring systems, light activated burglar alarms, and the many other electronic devices. So based upon that, many digital electronic devices we can prefer the logic gates, but main preference is that is done over the truth tables. So depending upon the requirement of the output and the truth tables and the different kind of operations. So what kind of output that is required. So depending upon that, the different logic gates that can be used, and these are the various kind of application of the logic gates. So next is the De Morgan's theorem. So what does it mean? De Morgan basically gives the different two theorem in order to define the combined gate. So in which we combine the two gates and we want to get their output value, and how their output value that can be represented in terms of other two gate like the XOR gate and the exclusive NOR gate. So how the NAND gate and the NOR gate that can be represented like that. So we are using over here the De Morgan's theorem. So De Morgan's theorem, depending upon that value, there are the two theorems are that. The first theorem is that it states that the NAND gate is equivalent to the bubbled OR gate. So what does it mean? Now the NAND gate that is equivalent to bubbled OR gate. So this is the output of the NAND gate. So that is equals to A, B inverse, and which is equals to A plus B plus. So what does it mean? So that means now the NAND gate that is a combination of AND and NOT. So this is a combination of these two and its value. Now for AND gate, the output is given by A and B, and this is for the NOT gate. So this is a combination of AND gate and NAND gate. Now this is equivalent to bubbled OR gate. So what does it mean? That is equals to bubbled OR gate. So that means we are combining here, this is the NOT gate and this is also the NOT gate. Means when two NOT gate inputs are bubbled with each other or they are combining with each other, they will give the same truth table over here. So that means the truth table is same in that case. So this is the first theorem. So that means now this A, so that means now here A into B, that can be written as A plus B plus. So this is known as the De Morgan theorem. But mathematically, when we represent, or in the matrix form, when we represent this A B inverse, that is equals to B inverse into A inverse. So this is quite different over here. So that means the analogically, when we, or the mathematically, when we represent A B inverse, that is equals to B inverse into A inverse, or you can clearly see that that is equals to A inverse into B inverse. But when in case of Boolean algebra or in the binary system, A B inverse, that is equals to A inverse plus B inverse. So now we will make here truth table over here. Now the truth table that can be maintained like this. So this is the output of NAND gate. Now truth table for this. Now when 1 is given to there and 0 is here, now what does that mean? So that means A into B, that is equals to 0, and output that will be equals to 1. Again when 0 is here, 1 is here, A into B, that is equals to 0, but output that will be 1. Again when this 0 is here, A into B is again 0, then we will get output over here. 1 into 1, so output that is 1, so 1 inverse that will be 0. So this is the truth table of NAND gate. Now make this table over here. Firstly calculate A inverse, then B inverse. Now A inverse of 1, that is 0, and B inverse of 0, that is equals to 1. Again that is A inverse and B inverse plus B inverse. Again we will get 1 over here. Now A inverse of 0, that is 1, again 0, then we will get 1 over here. Now the inverse of this 0, that is 1, inverse of 0, that is 1, again output 1 plus 1, that is 1 over here. Again inverse of 1 is 0, again inverse of 1 is 0, and in this case 0 plus 0, that is equals to 0. So that means now you can clearly see that the output in both of cases, here this value is same. So that means 1 1 1 0, and here the 1 1 1 0. So that means in both of them, both of the cases, output value is same. So this is the first De Morgan theorem, in which it is represented like that. That is equals to A B inverse, which can be written as A inverse plus B inverse. So this is known as the first De Morgan theorem. So according to first De Morgan theorem, what does it mean? The NAND gate that is equivalent to bubbled OR gate. So this is the first theorem. Now what is the second theorem? Second theorem, it states that NOR gate is equivalent to bubbled AND gate. Means NOR gate, what is a NOR gate? NOR gate, that is a combination of OR gate and NOT gate, and that is equivalent to bubbled AND gate. So that means A plus B inverse, that is equals to A inverse into B inverse. So that means firstly the NOR gate is what? And the bubbled AND gate. So NOR gate is, now the NOR gate is written as, that is equals to combination of OR gate plus NOT gate. OR gate is, this is OR gate, and for the NOT gate, that is equals to this one. So now plot the truth table for this. Now the truth table for this, that can be written as, now when 1 is here and 0 is here, and be 1, then 0 will be there. Now 0 is here, 1 is here, 1, that is 0. 0 is here, then 1 will be there, 0 is there. So this is the NOR gate. That means combination of OR and NOT gate. Now what is here? It states that the NOR gate that is equivalent to bubbled AND gate. Now what is a bubbled AND gate? So in the AND gate, the output that can be represented as like this. So this is the output over here, and the bubbled means we will take reciprocal to this. So this is known as the bubbled over here. So A inverse into B inverse. So that is equals to A inverse into B inverse. Now take reciprocal of this. Now reciprocal of 1, that is equals to 0. Reciprocal of that is 1 over here. Now again multiply, when you multiply these two, you will get 0 over here. Again reciprocal of this 0 is 1. That is 0. Again we will get 0 over here. Now that is 1, 1, and we will get output over here. Again reciprocal of this 1 is 0. Again this reciprocal of 1 is 0. Then 0 into 0, that will be 0. Again you can clearly see that the output value for these two, that is same over here. So that means when the output values are same, we are getting the same output. That means your truth table that is same for these two cases. So in this case we can represent it over here. So that means A plus B inverse, that means exclusive, this is the NOR gate that is equals to bubbled AND gate. So this is the second De Morgan theorem. So we can write it over here. So this is known as the second De Morgan theorem. So according to that, the De Morgan theorem is that. So first theorem is what? That means a NAND gate that is equivalent to bubbled OR gate. Because in both of the cases we are getting the same output value. So that's why NAND gate that is equivalent to bubbled OR gate. And in this case, second theorem is that NOR gate that is equivalent to bubbled AND gate. So in some of the logical or the digital devices, when we want to replace the NAND gate, so NAND gate that can be replaced by the bubbled OR gate, while the NOR gate that can be replaced by the bubbled AND gate. So this is the Boolean expressions for both of them. These are the important logical operations. That means in some of the digital devices, when we want to replace the gates, in that case, this A, B inverse that can be written as A inverse plus B inverse. That means this is the NOT gate of A and the NOT gate of B, and that is equals to OR gate. So this is the output of the OR gate. So that's why this is known as the bubbled OR gate over here. While in the second theorem, this NOR gate that is equal to bubbled AND gate. This is the output of the bubbled OR gate and AND gate. So in the AND gate, this is the inverse of A, that means the NOT of A and the NOT of the B, and this is the output for the AND gate. So this is known as the De Morgan's theorem. So now let us take a short break. After that we will start the what are the K values, how the sum of the products and the product of the sum, and these two signals are theorems are get used in order to make the output for the logical devices.
Now quality learning is easily available at your doorstep. S. Chand Academy brings detailed lectures based on AICTE curriculum as per the New Education Policy 2020. So do not forget to subscribe to the S. Chand Academy and access the wide world of knowledge conveniently sitting at your home. Stay connected and keep watching S. Chand Academy. Happy learning!
Now, in order to define the logical devices or the digital devices, basically some mathematical expressions are needed. So that mathematical expression for the Boolean algebra and that mathematical expressions which are used by using the minimum number of variables, that mathematical expressions, they are known as the K maps. Let us start. So what are the K maps? How we can define the different Boolean expressions by using the minimum number of variables in terms of K maps. So now introduction of K maps, or they are also known as a Karnaugh map. So now in many digital circuits and the practical problems, we need to find the expressions with minimum variables. That means we want to reduce the many variables and we want to calculate or define their expressions. Now we can minimize Boolean expressions of 3 and 4 variables very easily using the K maps without using any Boolean algebra theorems. We know that the Boolean algebra theorems are basically, they are known as a De Morgan's theorem, which are basically used to, they are used for the replacement of the gates, by which output values that can be replaced in terms of either AND gate or the bubbled OR gate or the bubbled AND gate. So they are also the simplest way, but in the K maps, we can find out the expressions or the output value that can be done without using their that expressions, and the variables that can also be reduced. So in this case, we are using the minimum number of variables are used over here. So K map can take two forms. One is a sum of product, that is known as a SOP form, and second is known as a product of sum, that is known as a POS form. So SOP and POS forms are used according to the need of problem. The K map, that is a table-like representation. So in this case, table-like representation is done. So depending upon the number of blocks used and the number of variables that are get defined. So when we are defining over the larger circuit, the number of variables that can be reduced in that case. But it gives more information than the table. We will fill the grid of a K map with zeros and 1, then solve it by making the groups. So in this case, groups are basically maintained in order to get the output value of this as sum of products and the product of sum. So it will given in the two forms over here. So that means the Boolean expressions, when we are over the larger number of the digital circuits, so in that case, there instead of A and B variables, there the large number of variables are present. But in order to define the output from that, and these variables are get reduced, we want to use a minimum number of variables, and that variables that can be defined in terms of some table, and that table in that table we can take firstly the products, then some of them that will be taken, or firstly we can use their sum, then their products that can be taken. That means in the SOP form and the POS form that can be used. So that kind of tables, they are known as the K maps. Now steps to solve the expressions using the K maps. How we can solve the K maps, that means how the digital devices or digital circuits that can be solved in order to get the output value. Firstly, select the K map according to the number of variables. So depending upon the number of variables, some K maps they are given over there. So depending upon the number of variables, either there are 3 variables, 4 variables, or 5 variables. So depending upon that, K maps are introduced. Then identify the min terms and the maximum terms as given in the problem. So in the given problem, when the minimum terms that can be also identified, and the terms which are having the maximum value, they are also identified. For SOP, put ones in the blocks of K map respective to the min term 0 elsewhere. That means when we are solving the SOP map, in SOP map, the terms which are having the maximum value, their value is given to be as 1, and the terms which are having the minimum values, they are given as a 0. So SOP, that means in the sum of products that can be used. While for POC, puts 0 in the blocks of K map respective to maximum terms and ones elsewhere. That means in POS, that means in the product of sums, the different kind of things are used. So that is totally opposite to the SOP. In the POS, when the maximums are there, we are using 0, and when the minimums are there, we are using only 1. So that means these are reciprocal to each other. So SOP, that means the minimum terms, ones that is respected to the minimum terms, otherwise 0 is represented elsewhere. So both are opposite to each other. Third one, then fifth one is a make a rectangular group containing total terms in power of 2 like. That means 2, 4, 8 except 1. So that means even number of blocks are used over here, and try to cover as many elements as you can in the one group. So one group is formed and we want to accommodate more of the elements into the one group. And from the groups made in step 5, find the product terms and the sum terms, and then we will use them in the SOP form. So that means in the SOP form, firstly product terms are solved, then their sum is get done. While in the POS form, firstly sum terms that will be identified, then their products that will be get given over here. So this is the SOP form and the POS form. Then how we can solve these variables. So K-map, they are used to define, to solve the digital circuits. So the main thing is that firstly we want to put the 1 in the min terms and then 0 for the elsewhere, while in POS term we want to put the zeros in the max term and then we will have to put the 1s elsewhere. So this is the important terms in order to solve the K-maps. Now next is this is the sum of product, that means SOP form. So in this case, so SOP form, so that is represented as, so 8 blocks are there. So in this case, there are 8 blocks, that is equals to 1. There is no variable is there. When we are taking only the 4 blocks are taken, in that the 4 blocks. So if these are the 4 blocks over here, so only one variable is present. When we move from one block to another block, so one variable that is changed over here. So that means when we move from this to this, here C variable is there. And when you move from here to here, again the C variable is there. So one variable is there. One in the 2 blocks, they can be represented as the, when we are taking only the 2 blocks are taken over here, so there the 2 variables are changed. So we know that when we move from here to here, or you can move from this to this, so 2 variables are changed. And one block, the 3 variable terms. So different terms are defined in this case in order to solve this SOP term. So SOP that can be solved over here. Now then next is the product of sum. So in the product of sum, so in that case, firstly the sums are taken, then their product is given over here. So that means firstly we will take the sums, then their products are done. While in the SOP form, firstly we will do the product of the terms. So product is done, then the sum is done over here. So that is known as the SOP form. So these will represent the product of these variables. So product of these variable and the outputs are given over here. While in this case, the sums are given firstly, then their products are defined over here. So in this case, firstly we will define the sums over there, then the products are defined. So these will represent the sum of these variables over here. Then depending upon that, these are defined as a number of variables over here. So depending upon that, then their products are done, and we will give the output that will be obtained in this case. So this is known as the K-map values. So in the K-maps, basically they are used to define the whole circuit that can be defined in the minimum number of variables. That means the large variables that can be reduced in this case. So only in this one block we can represent the whole system or the whole digital circuit that can be defined in this case. So by depending upon these terms, some of another terms that can be defined, that is known as the logic IC. So what is logic IC? Again, this is a simple semiconductor device that implements a basic logical operation that is performed on one or more digital input signals, that it can be represented by either 1 or the 0 or H and L to produce a digital output. So that means there is a truth table of N, that is a NAND gate. When there is no input, then we will get, because reciprocal of this is done. So here in this case, instead of 0, we are writing L over here, and instead of 1, we are writing H over here. That means high or low value that can be done. So these kind of circuits, they are known as the logic ICs over here. So the logic IC, that is a semiconductor device that implement a basic logic operation that is performed on one or more digital input signals to produce the output signal. That means over the input signal, some of the logical operations are done and we will get the output signal. So that is known as the logic IC. Or you can say that the combination of different logic gates that will give us some circuit, that is known as the logic ICs. These are the typical applications of the logic IC. They can be used in the gates, buffers, flip-flops, counters and the multiplexers. So these are the different functions of the logic ICs. So depending upon that, the logic ICs, that means these are the semiconductor devices. So depending upon that, in different kind of these things, we can use this logic ICs to give the different circuit diagrams. Till now we have understood what is the K-maps, how the K-maps are used to perform the form the different kind of devices, and by reducing the different variables to the minimum number. So by using that in the SOP and the POS kind, the different kind of logical circuits that can be designed in the K-map values, and the logic ICs, they are used to define the how we can form the different semiconductor devices that can be formed by using the different logic ICs. Thank you.
If you want to study this topic in detail, refer to the book by S. John Publishing. Link is provided in the description box. If you found our video interesting, please like, share and subscribe. And do not forget to press the bell icon.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.